So we'll start with the Matthew Flinders Medal and Lecture. This award recognises scientific research of the highest standing in the physical sciences and honours the contributions of Australia's early scientific researchers. It's our highest award in the physical sciences. And I'm proud to announce that the 2013 Matthew Flinders Medal and Lecture is our fellow Professor Ken Freeman. Can you please come up, Ken? Ken is the Duffield Professor of the Research School in Astronomy at Astrophysics at the ANU, and I'm going to invite him to the stage to give us his lecture.
Professor Freeman is widely acknowledged as one of the world's most eminent galactic astronomers. The first to identify the necessity for dark matter in galaxies, he has shaped our current understanding of the dynamics and structures of galaxies. Over the past decade, Professor Freeman has co-established the field of galactic archaeology, where fossil records of stars are used to trace the formation of the Milky Way. His ideas have helped launch the $1 billion European satellite Gaia, Global Astrometric Interferometer for Astrophysics. Gaia will work with a purpose-built instrument on the Anglo-Australian telescope to fossick for stars that will chronicle the history of the galaxy since its birth more than 13 billion years ago. Professor Freeman has supervised more than 50 PhD theses, and he truly is a father of Australian astronomy. Professor Freeman, congratulations. Now I invite you to present your address entitled Dark Matter in Galaxies.
Thank you, Jagadish. Well, good morning. I'm very grateful to the Academy for honouring me with this lectureship. Thank you. Early in my career, I was studying the theory of how galaxies rotate, and I noticed some anomalies between what the theory predicted and the observations. It seemed that there was much more matter in spiral galaxies than we could understand, and my work became part of the discovery of dark matter in galaxies during the 1970s. Many people were involved in an exciting decade of research in which our understanding of galaxies and the universe underwent a major transformation. We're gradually learning more about the properties of this dark matter in galaxies and how the dark matter that we see now in galaxies relates back to conditions in the early universe. And this Matthew Flinders lecture will be a quick overview of dark matter in galaxies. So here are two spiral galaxies like the ones that we live in. They're flat objects, one of them's seen edge on, one's seen face on, and they're flat and they're spinning. And the universe is made up mainly of galaxies like this. Most of the stellar mass is like this. But what you're seeing here is only about 5% of the total mass. The other 95% of it is in some dark form that we know is gravitating, but we don't know what it is. So here's our galaxy, as seen from space, not too far from the Earth. The stars of this galaxy lie mostly in a flat disk that's arrowed there, and about 25% of it lie in a central bulge. So those are the two main components of the galaxy that we can see. There's a very important component that we can't see at all, and that's what's called the dark halo. How do we know it's there? Well, almost all galaxies have one of these dark halos. We see it only through its gravitational effect on the way that these galaxies rotate. Oops, here we go. Okay, so what you're seeing here in this plot is the rotational speed of the galaxy as a function of the radius in the galaxy. Now, we use arcane units of length called kiloparsecs, but don't worry too much about that. But the sun, if we were living in this particular galaxy, the sun would be about where the arrow is. When we work out how this galaxy should be rotating, they're not rotating as rigid bodies. They're rotating more like water going down the plug hole. There's a lot of shear. When we work out what we'd expect to see, it's really more like this. We can calculate what we expect to see, and that's what I did long, long ago. What we actually see is a galaxy rotating like this. So there's much more rotation at large radii than we can understand from the gravitational field of the gas and the stars alone. And the way we measure these rotation curves, here's a picture of a galaxy. You can see the little spiral path of the galaxy, that's the optical part here. All this blue stuff is gas, it's neutral hydrogen. The neutral hydrogen goes far beyond the stars. It's moving almost perfectly around this galaxy in circles, and we can use this hydrogen to measure how fast the galaxies are rotating and hence measure the gravitational field in the plane of the galaxies. Neutral hydrogen we can't see with optical telescopes. It radiates at a radio wavelength of 21 centimetres, 1.4 gigahertz, and we can measure its velocity of rotation at every point using the Doppler shift with radio telescopes like the Australia Telescope Compact Array at Narrabri that you can see in this picture. Rotation has now been measured for several hundred spirals, and we always find that the gravitational field is much stronger than expected from the stars and the gas alone. The stars and the gas provide only about 5% of the measured gravitational field in the outer parts. The remaining 95%, this enormous fraction, comes from something dark, and we don't know what this is. It's one of the biggest problems in astrophysics today, trying to understand what this dark stuff is. In the 1990s, we thought that dark matter might be in the form of dead stars or failed stars. We mounted a big experiment, I'll mention it again right at the end, but that turned out to be wrong. The discovery of dark matter in the 1970s led to the current ideas about how the galaxies form from dark matter and gas in the early universe. It was a real paradigm shift. And I really mean paradigm shift. It completely changed our ideas of what was in the universe and how the universe worked. We thought originally the universe was made just of baryons. After the 1970s, we realised that the baryons were just a minority fraction. So early in the life of the universe, matter was fairly smoothly distributed with very small random fluctuations in density. And these fluctuations grow just simply under the influence of gravity, and small objects merged to form larger objects in a hierarchy of merging. Now, this dark matter on a galactic scale has to be cold, when all that means is just moving slowly relative to the expansion of the universe. It has to be cold in order to condense into galaxy-sized lumps, galaxy-sized dark halos. And then the baryons condense in these dark halos to form the disk. If the dark matter was moving fast, it wouldn't be able to condense into the galaxy-sized lumps that we see. And this dark matter is called cold dark matter, or it's usually called CDM. Our whole understanding of the way the universe evolved is based on this concept, which really grew out of the work of the 1970s. And here's a computer simulation of the cold dark matter structure of the universe. Now that grew out of tiny fluctuations, and you can see now that there's this whole web of structures. Now these just arise spontaneously through gravity, and these condensations are clusters of galaxies and individual galaxies themselves at the intersections of these sort of filaments. So how large and massive are the dark halos of large spirals like the Milky Way? Well, the flat rotation curve that we see here, you'll see this a few times in this talk, velocity against radius. These flat rotation curves, you can just go through the very simple dynamics, and they mean that the mass of the galaxy increases linearly with radius. The acceleration you need to go around the circle is velocity squared divided by r. The gravity goes like the enclosed mass inside r divided by r squared, just Newton's law, a little bit of algebra, and you see that the mass increases linearly with radius. So that's the enclosed mass inside r, just keeps on going up. So for the Milky Way, the galaxy we live in, the mass out to a radius of r kiloparsecs is about 10 to the 10 times r in solar masses out to about 50 kiloparsecs. And remember that the sun is at about 8 kiloparsecs. So you can see there's quite a lot of dark matter out even to the solar radius, but as you go further and further out, this just keeps on going. We know it keeps on going to at least 100 kiloparsecs. It can't go on forever because this would give us an infinite halo mass. Halos must have a finite extent and mass. How large are they? Well, the Andromeda galaxy, called M31, and the Milky Way are a bound pair of galaxies, and they provide a good test of just how big these dark halos are. So here's a picture of the local group. Now we live in a small group of galaxies. There are two big ones, the Milky Way, that's us, and Andromeda, it's about the same size, and we have a few small galaxies around them, and then a whole bunch of tiny dwarf galaxies. These two galaxies absolutely dominate the gravity of the local group. There was a wonderful paper in 1959 which used the relative motions of M31 and the Milky Way to work out how massive dark halos actually are. M31, Andromeda, and the Milky Way are now approaching at about 120 kilometres a second. Their separation is about 750 of these kiloparsecs, and the age of the universe we now know is 13.7 gigayears, but we've sort of roughly known that for a long time. Now, the universe is supposed to be expanding, but these two galaxies are contracting. They're approaching each other. What's happened? Well, what's happened is that these two galaxies formed together, started expanding with the expansion of the universe. They had enough mass to turn this expansion around, and now the two galaxies are approaching. Dynamics is very simple. You've got all the facts you need to work out how much mass is involved. You can work out what the Milky Way's share is, and at least 120 times 10 to the power 10 solar masses. Sorry about these astronomical numbers, but you've met them already yesterday. Now, the stellar mass is only about 6 by 10 to the 10. The total mass is 120 times 10 to the 10. And that's what's telling you very directly that only about 5% of this mass is stellar, and all the rest of this stuff is in some gravitating form that we can't see. So it tells us that the dark halo must go out to at least 120 kiloparsecs, far beyond the disk's radius, which is about 20 kiloparsecs. Now, this paper was published in 1959, and like a number of the really fundamental papers in this whole dark matter saga, it came at a time that was just too early for people to accept. So again, it's always this problem. What you do when somebody comes along and says, your galaxy is 20 times more massive than you think. I mean, what do you do with that sort of information when you have no pre-existing theoretical framework in which to insert it? Well, that's what happened here with this Kahn and Vulture paper. It's a really important paper. It's absolutely correct. There's been more work done on this in the recent, just in the last few years. What they did was absolutely right. The paper was almost ignored. Okay, so we're in a situation now where the dark matter extends 5 to 10 times further out than the disks of these galaxies. So here's a picture of our little galaxy, the luminous part, immersed in this enormous dark halo. Of course, it doesn't have a sharp edge, but it's too hard to make these things fade away. So, in terms of actual matter in the universe, the dark matter makes up about 84% of the matter in the universe. I'm not talking about dark energy here, I'm just talking about matter. So about half of this dark matter is in galaxies, and the other half's in intergalactic space, uncondensed. The remaining 16% of the matter is ordinary baryonic matter, like what stuff that you and I are made of and fills the Earth. Okay, now I want to talk just briefly now. I've been talking about really big galaxies. Now I want to talk about little galaxies, because I'm going to come to something that's, I think, may be quite interesting. So we looked at big galaxies. Here are, I'm going to show you two kinds of very small galaxies. So you remember our galaxy had a total mass, a total stellar mass of about 10 to the 10, 6 by 10 to the 10 solar masses. This little guy is only 1 million solar masses, 4.5 orders of magnitude smaller. This sort of dwarf galaxy has got no gas, just stars and an awful lot of dark matter. Some of these are so faint that they're almost invisible. These faint galaxies aren't rotating, but we can still estimate the mass by using not their rotation, but just the velocities of the individual stars. These galaxies are made up almost of pure dark matter. Some of them have less than 1% of their mass in baryons, compared with the cosmic fraction, which is about 16%. So these little guys have lost, or maybe they never even acquired, almost all of their ordinary matter, their baryonic matter. Here's another sort of dwarf galaxy, similar mass, just a tiny little thing. This one's got stars and a lot of gas. You can see stars forming. All these splotches are stars. Stars, gas, and a lot of dark matter. This tiny galaxy is 10,000 times fainter than our Milky Way, but its dark matter is 1,000 times denser. And the reason why its dark matter is so much denser is that these little galaxies are the first things to drop out of the expanding universe. They form very early, when the universe itself was very dense, and their density of dark matter is just reflecting the density of the universe at the time when these little guys dropped out. So what I want to do now is compare the properties of the dark halos in these little galaxies with the dark halos in the big galaxies. The dark halos of galaxies appear to have constant density cores. So in the centre, it just means the dark matter density is pretty much constant, and then after a while it starts to tail off. We can model these density distributions just with a simple form. Rho is the density as a function of radius, and it's just some central density divided by 1 plus r over rc squared. And we use this simple distribution because it gives you those flat rotation curves that we observe. So here we go back to this rotation curve. We can use the rotation curves of disk galaxies to measure how dense their dark halos are. And it's very simple. Here's the rotation curve of the galaxy. This is what we expect from the disk and the contribution from the gas. They're nowhere near enough to give us the rotation curve we observe, so we have to add in another component that we can't see except through its gravity that will have a rotation curve like that. And when we add all these things together, we have to add them quadratically, then you get the observed rotation curve. The important thing here is that the slope of this rotation component from the dark halo, that slope gives us very directly the central density of the dark halo that this stuff is moving in. So this is a very direct and simple thing to do. When we go to the faint galaxies, we haven't got the rotation. They're supported against gravity mainly by the random motions of their gas and stars and not by their rotation. We can still measure the central densities of the dark halos. It's a little more indirect, but we can still do it. When we look at the random motions of the stars in these little galaxies, we just plot the random motions against radius. So it means we're looking at some radius in the galaxy, and we see some stars coming towards us, some stars going away from us. We measure how much random motion there is in what we see, and we just plot it against radius. Now, I don't know if you remember, the rotation of the big galaxies was typically 150, 200 kilometres a second. Here, we're looking at random motions that are only 5 kilometres a second. They're tiny because these galaxies are very small. But the thing you see is that the random motions don't change much with radius. Again, they're flat. In the little gassy dwarf galaxies, the baryons are mostly in the form of gas, just neutral hydrogen. And now we can use the random motions of the gas, which again is usually constant with radius. Now there's a it's sort of a lucky thing, but it's not really lucky, it's just the way it has to be. But the lucky thing was that to measure the central densities of the dark halos, we need to know the radial distribution of the stars or of the gas. When we look at the stars in these little dwarf galaxies, the dwarf spheroidal ones, or the gas in the dwarf irregulars, they're observed to have simple Gaussian radial surface density distribution. So if we plot the surface density distribution, just the amount of mass per unit area, we see that it's got this Gaussian form, just like e to the minus r squared over some length squared. Now it was not absolutely essential, but that's how it's come out. If we take the logarithm of that, just the ordinary logarithm, natural logarithm, then log of that surface brightness just goes like minus r squared over a squared plus a constant. I'm going to show you some of these in just a second. Having a Gaussian surface density distribution is a very convenient thing because it makes our analysis easy, because then the volume density, it turns out, is also a Gaussian. It's just a little bit of algebra to show that. So here's one of these little stellar dwarf galaxies, the Carina dwarf galaxies, and I'm plotting the logarithm of intensity against radius squared. Now that should be a straight line if the distribution is Gaussian, and you see how well it is approximated by a Gaussian. Now I'm going to go to the other sort of the dwarf galaxy, the gassy sort. This is this little guy that we saw before. Surface brightness of the gas, log of the surface brightness of the gas against radius squared, and again, you see it's almost a perfect Gaussian. Now that's terrific because, in fact, it's no accident. It's what we expect for stars and gas with constant random velocities in the central flat density core of a much larger dark halo. So we have a little dwarf galaxy, the stars and the gas, sitting in the centre of a much, much larger dark halo. So now, if sigma star is the random velocity of the stars or the gas, and this A star is the Gaussian length for the density distribution of the stars or gas, this thing we had here, then it's very simple to get the central density of the dark halo. density is just 3 sigma squared over 2 pi g gravitational constant divided by a squared. So it's a very simple thing. So what's happened here is that we can get the central density of the halo by just knowing the properties of the tracer material, stars or gas, moving in their gravitational field. So now we have the central densities for the dark halo of the bright spirals, and we've got central densities for the faint dwarf galaxies, both the stellar sort and the gaseous sort. And the question now is, and this I'm getting towards the end of what I want to say, the question now is, how do the halo densities change from bright galaxies to faint galaxies? So the red and blue points are just 2 different ways of measuring central densities for the dark halos of bright galaxies. And what I'm plotting here is just the log of the central density of the dark halo, and again, that's our astronomical type units, solar masses per cubic parsec, but I'm plotting those densities now against the brightness of the galaxy, and again we use terrible units, they're called magnitudes, but all it means is that these are the bright galaxies and these are the really faint galaxies. And what you can see happening is that the spirals have relatively low densities of their dark halos. It's what I was telling you before. Here are the dwarf galaxies, these quite high densities, and see we have more than 3 orders of magnitude of difference in the densities between the dark halos of the spirals and of the little ones. The faint galaxies have these much denser halos, close to a solar mass per cubic parsec, much like it's in fact 10 times higher than the galactic disk near the Sun. These galaxies formed very early in the life of the universe, when the universe was much denser, and that's why their halos are so dense. Well, what is dark matter? Well, we don't know. We did a monumental experiment during the 90s at Mount Stromlo called the Macho experiment. I won't go into the details of this. I'm happy to talk to people. But we were able to show that what dark matter is not is compact objects like stars, dead stars, planets, with masses between about 1 over 10 million of the mass of the Sun and 30 times the mass of the Sun. And that excludes most kinds of dead stars, neutron stars, white dwarfs, or very small stars that tried to start but weren't able to keep going. They're called brown dwarfs. So the most likely candidates now for cold dark matter are weakly interacting massive particles, most of which have not been seen in the laboratory, things like with names like axions, neutralinos, but they're objects left over from the Big Bang. If the dark matter particles are neutralinos and their masses are around 100 gigaelectron volts, then it is conceivable that they could be detectable by gamma rays emitted when these neutralinos annihilate. And the best place to look is the place where the density of dark matter is the greatest, and it's in these tiny galaxies that I was telling you about, where the densities of the halos are really 3 orders of magnitude higher than in the big galaxies. There are searches going on with gamma ray telescopes on the ground, like the HESS telescope on the High Plain in Namibia, and the Fermi Space Mission. But so far there's no success, but we have high hopes that something will turn up in the not too distant future. Thank you very much.
Are there any questions or comments to Professor Freeman? Mike.
Mike Doppiter, ANU. Ken, a few years ago, you published a review which I found produced a quite extraordinary result, which you didn't even mention actually today, and that is that that although these dwarf galaxies have got very high volume densities, their surface densities are effectively identical for all galaxies. And that seems to me to be saying something very profound about the nature of dark matter. Would you care to comment?
Yes, that's good. It's something I would have liked to have talked about, but time prevents. What Mike is talking about is, although the densities of these dark halos are very high, they're actually rather small in space. And there's a correlation between the density, the central density, and the size of these halos such that it actually balances out. And the surface density, the amount of, say, solar masses per square parsec, is actually the same for big halos and for little halos. And that's actually quite a profound result, because it goes right back to the very early universe, the particular nature of this fluctuation. and it tells us what the power spectrum of the initial fluctuation field is that this matter came to us. I showed you a picture of all this filamentary structure coming out of the computer simulation. Well, the spectrum, the spatial spectrum of those fluctuations is directly linked to that correlation that you mentioned. So it all ties together in quite an interesting way.
Are there any further questions or comments? John.
You mentioned that the dense neutrino fell out, I think, and got left behind or something, I guess, during the expansion. I have no idea how that sort of can happen. Can you explain?
Yeah, I'm no expert in this either. But when you come out of a very hot and very dense universe, different objects fall out at different stages. Photons drop out at certain places, baryons drop out, neutrinos, neutralinos, at different densities and different temperatures. And it's just the nature of the particle has associated with it an energy and a temperature, and that when the universe gets to that particular temperature, then these various things fall out. But I can't tell you much more than that. There are plenty of particle physicists in the audience who can tell you much more.
What do you think, Ken, of explaining your observations by modifying the laws of gravity rather than introducing dark matter particles? Do you have any views on that?
Yeah, I do. I'm going to mention that a little bit tonight. I don't know if you're coming to the dinner, but there is an alternative theory of gravity, just very briefly, in which when you get to these very low accelerations we get in the outer parts of galaxies, that the nature of the law of the gravitational law changes. It changes from being an inverse square law that we're used to an inverse one law. Now, the only evidence, really only strong evidence for this, observational evidence, is just the rotation curves, and this is a way to get out of the dark matter problem. It's a huge subject. It's been very difficult to disprove it at the level of galaxies. It's easier on larger scales, but I can talk to you more about that if you wish.
Okay. On that note, could you please join me to thank Professor Freeman for a fascinating talk?